Welcome, Calc students, to our third part of section 1.3, where in this video we're going to go ahead and address what's called the squeeze theorem. The squeeze theorem is something we use when we're trying to find the limit of a particular function where other methods aren't working, but it turns out that the function whose limit we're trying to find happens to be squeezed between or sandwiched between two other functions. So the y values of f are less than or equal to the y values of g, but at the same time greater than or equal to the y values of h. So just to be clear, that interval is an interval of y values. And this is happening on some interval containing an x value of c, so that c is an x value. And it could possibly be that at c itself, f of c maybe doesn't exist. That could be one reason why we are having to use the squeeze theorem to find the limit. So f of c does not have to exist in order for us to use this theorem. So all that has to be true to use this theorem is that the function in question is always less than or equal to the y values of some upper function, but greater than the y values of some lower function at the same time. And what has to be true is that the limit as x approaches c for h would equal L, which is the same thing as x approaches c for g. And so if that is also true, if the left function has a limit, if the lower bound function reaches the same limit at c that the upper bound function does, then the middle function will be forced to approach the same limit as well. Now, some textbooks refer to this theorem as the sandwich theorem. So sometimes this theorem is referred to as the sandwich theorem. So those of you that might end up taking calc again in college, or when you take a higher level calc and they refer back to this, they may refer to it as the sandwich theorem. These are one and the same: squeeze theorem, sandwich theorem. So let's take a look graphically at what this statement is saying. So here we have our middle function f of x, okay? Notice that the y values, so the vertical position of g is higher than f, right? The y values of g are all greater than the y values of f, and then the y values of h are all less than the y values of f. So it's squeezed in between these two functions, if you will, in a graphical sense. Now, if you look along the horizontal axis, you'll see, okay, let's look at this h function. As I approach h from the left, as I approach c from the left along the graph of h, and also from the right, I can see that it's approaching this y value of L. And similarly, on the graph of g, as I approach the x value of c from the left and the right, I can see that my g of x graph is also approaching the same y value as h. So graphically, the h graph sort of came up to a y value of L and then went away, whereas the g value dropped down to a y value of L and went away. Meanwhile, the function that's squeezed in between the two was forced to also hit a value of L right at that x value of c, because it's being sandwiched between or squeezed between its upper bound and lower bound functions. So here you can see, okay, yes, f of x is indeed greater than h, but less than g, right? G was higher than f, which was higher than h. And I could see from the graph that as x approached c on the h graph, it equaled L, as did the graph of g as x approached c. And so I can also see from this graph that as I approach c from the left and right of f as well, or on the graph of f, as I approach c from the left and right, it also had no choice but to approach L. So that's how it got its name. Now let's see how it would be used. So on the AP test, when they ask you to find limits using the squeeze theorem, they're looking more for a justification. So I'm looking for you to put these answers more in paragraph form. But each little paragraph that you create will be following three key pieces. So you'll want to keep those three key pieces in your mind the first piece that you're always going to want to reference is that given inequality. The second thing you're going to want to show are the limits for the lower and upper bound functions. And then the last thing you're going to want to write is your conclusion. So over here, I'll show you what that looks like in paragraph form. So you kind of want to start by saying this, since, and then you state what's given, right? We know that 8 minus x squared is less than or equal to f, which is less than or equal to 8 plus x squared. So we start with this given information to point out that the function f has to always be less than 8 plus x squared and greater than 8 minus x squared. And you kind of begin by saying, since this is true, and since, and then this is where you find your limits. The limit as x approaches 0, in this case, that was the c value in question. We're trying to find the limit as x approaches 0 of f of x. So since the limit as x approaches 0 of the lower bound function, and I just work that limit out by substitution, and that equals 8, and the limit as x approaches 0 of the upper bound function, which I'll just solve with substitution, so that also equals 8. So then you've established that f of x is the middle, right? You've established 8 plus x squared as the upper bound, 8 minus x squared as the lower bound. Now what you've established is that this lower bound is coming up to 8, and the upper bound is dropping down to 8. So then, therefore, this is your conclusion. And then you always want to reference the name of the theorem in your conclusion. Therefore, by squeeze theorem, the limit as x approaches 0 of the middle function must also equal 8 as well. So that's kind of like your last sentence, but all of this is the whole answer. So just recapping, you begin with that inequality that's typically given. Sometimes you might have to set it up. And when we practice for AP tests, well, I'll try to find ones that are like that. And then you kind of go on, you show some work for the limits of the upper and lower bound functions, and you want to show that they're the same. Okay, so that's your limits, and you kind of write it in paragraphs since this is given, and since this is that limit, and that's that limit, and then you end with your conclusion, which is where you say, therefore, and then you want to reference the name of the theorem, and then you state how that middle function's limit must also equal the same 8 that the lower and upper bound functions equaled as well. So these are the things I will be looking for when I grade these questions. Paragraph form, starting with that given inequality, continuing with your limits, and concluding with the final statement. Now, one point of clarification that I want you to keep in mind moving forward is that these functions right here are not to be confused, with left hand and right hand limits. So this will become more important as we move into section 1.4, which gets into that idea of left hand and right hand limits. So once we start learning about those, don't confuse what's happening in the sandwich theorem or the squeeze theorem with that. So this is not a left hand limit or a right hand limit. These are upper and lower bound functions. These are two completely different functions, one that's greater than f and one that's less than f. And so when I find these limits, these are not left hand, right hand limits. These are two completely different limits of two completely different functions that just happen to be the same thing, because in this case the lower function is coming up to 8, the higher function is going down to 8, and in between there's this f of x that they're squeezing to reach the same value. So it's upper bound, lower bound, squeezing the middle into the same number. It's not a left hand or right hand limit. So please write that down and remember that moving forward. Okay, but now let me go ahead and walk through part B. Part B looks a little weird because everything here is a variable, but notice the only letter written inside f is x. So that means of all these letters, we only treat x like the variable since this is a function of x. And it's going to be approaching the value of m in this particular case. So I'm going to start with the same paragraph form as I did the last one, and I'm going to keep these same three things in mind: inequality, limits, conclusion. So I'm going to start by saying, since this inequality is true, this inequality that I was given, so since f of x is greater than or equal to p minus the absolute value of x minus m, but less than or equal to p plus the absolute value of x minus m. So since that is true, how do I know that's true? Because it's given. And so now I'm moving into my limits. And since the limit as x approaches m in this case of p minus the absolute value of x minus m, so I'll find that limit by substitution. And so that ends up being p minus 0, which is p. And we've got the limit as x approaches m of the upper bound function, p plus the absolute value of x minus m. So I'm going to, again, solve this by substitution. Oops, sorry, that should be a minus right there. I get p plus 0, which is still p. So it turns out that, so f of x is stuck between these two functions. This is the upper bound, this is the lower bound, but at m, at the value of m, the lower bound function is approaching the same exact y value as the upper bound function. So therefore, this is where squeeze theorem comes in. We'll say the name by squeeze theorem, and then we'll make the conclusion. The limit as x approaches m of that middle function must also equal p as well. And this whole thing is the answer, this whole paragraph. So what I'd like you to do now is try. Go ahead and pause your video here. Try these two examples here, A and B, and then come back to the video to check your work. Hey guys, okay, so for the first part, A, you want to start with that inequality, which says that g of x is trapped between the 2x squared plus 5 function on the top and the negative 2x squared plus 5 function on the bottom. You start with that. Okay, so since that's true, and since these limits, the lower bound had a limit equal to 5, the upper bound had a limit equal to 5, so they're equal, they're approaching the same thing. They're pushing the g function to approach the same thing they are, and so then you end with that conclusion. All right, therefore, by sandwich theorem, and by the way, you can abbreviate. You can call it ST, and that's also true for the AP test. You're allowed to abbreviate there as well. Then you say, okay, that middle function must also have the same limit. For the second one, you start with that inequality that's given. So since this is true, right, h of x is in between the y values of absolute value of x and the y values of negative absolute value of x. And since those upper bound and lower bound limits are both approaching 0, so this one's dropping to 0, this one's coming up to 0, therefore, right, reference that theorem, don't forget to put ST, the limit as of h as x goes to 0 is also 0 as well. Okay, so moving to example 2, this one gets a little bit harder. So first it wants us to kind of visualize what's going on. So use the graphs to observe the squeeze theorem visually, and then find the limit as x approaches 0 of f of x. Notice that no inequality was given here. So this is a situation where we're going to have to start with our own inequality to start. But why don't we go ahead and take a look at the graph of this function really quick. So here I've got the graph of the absolute value of x. That's the one in blue. You can see that is the upper bound function. Then I have the graph of negative absolute value of x graphed, and that's the one in red. You can see that's my lower bound function. And then this one in green is the graph of the absolute value of x times sine x. And you can see that the y values of this graph are always less than absolute value x and greater than negative absolute value x. And these two absolute value functions want to go to 0 as x is approaching 0. So they're squeezing the absolute value of x times sine x function and making it also go to 0 at that same point as well. So we know that that's what the limit should be graphically. Now how we prove that analytically is by using the squeeze theorem and using another well-known feature of trig functions, which is this. I'm going to take those off for a second. But we know that if you look at the sine of x graph, and you look at the graph of 1 and -1, we know that the sine of x graph, the range of it is stuck between 1 and -1, right? We remember this about sine, and this is also true of cosine. Their range is between 1 and -1. So that's the interval that we are going to start with on this problem. Okay, so we are going to start with the given inequality, and we're going to say since -1 is less than or equal to sine of x, which is less than or equal to +1. So we had to start with our own interval, and we went with what we knew to be true about just the sine function. Now what I'm going to have to do to get to here, right, because I want my middle function to be the same as f of x, I need there to be an absolute value of x in there. So what I'm going to do is multiply the absolute value of x to each part of my inequality. So I'm just going through the inequality. I'm using multiplication property of inequality. I'm multiplying by an absolute value so it won't turn the signs around. The signs will stay in the same direction. But what it will do is it will introduce an absolute value piece into each part of my inequality. Okay, so now I have this. So since the range of sine is between -1 and 1, and since I can multiply each piece by the absolute value of x, then this inequality also holds true. The negative absolute value of x is less than or equal to this function, which is less than or equal to positive absolute value of x. And we knew that to be true because we just witnessed that on a graphing calculator a second ago. So since this is true, and now I'm going to go ahead and find my limits, since the limit as x approaches 0 for the negative absolute value of x equals 0, and the limit as x approaches 0 for the positive absolute value of x is also equal to 0, then therefore, by the squeeze theorem, I'm going to abbreviate here, we can say that the limit as x approaches 0 of that function that was squeezed in the middle, which was absolute value of x times sine x, we know that that limit would also be 0 as well. So that's what was happening kind of right here. The positive absolute value function was coming down to 0, to the left and right of 0, and the negative absolute value function was coming up to the y value of 0 as x approached 0, and it forced this oscillating function to also go to 0. And that's how you would do that proof. So we would introduce an inequality that we know to be true, multiply in the remaining pieces that we need to form our full function, which creates new upper bound and lower bound functions, and then we find the limits of each of those, which should be the same, and then we can make the statement saying that the limit of our middle function is also the same. So why don't you guys go ahead and try this last one, pause the video, work it out, and then check back with the video to see if you got it right. Okay, so for this one, it might have thrown you off a little bit that this was a regular x instead of absolute value x, because we do have to, we do need to make sure that the upper bound and lower bound functions are negative absolute value of x and positive absolute value of x, which it kind of hints at here. So it wanted us to graph it with these two functions. And I'll show you that graph in a second, and then visually kind of realize that these are the upper bound and lower bound functions. So it's okay in this scenario, since you're given that hint to look at it graphically, you can then make your conclusion based off the graph that this function, even though this x is not an absolute value, this function, as you'll see, is still trapped between positive absolute value of x and negative absolute value x. So it's okay to start with that statement based on the graph. And you could even say something like this: since graphically the negative absolute value of x is less than or equal to, blah, 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 and then we find the limit of the lower bound function, the limit of the upper bound function. As you can see, they both go to 0. Therefore, by squeeze theorem, the limit of that middle function must also go to 0 as well. Now, let's take a look at the graph. Okay, so again, I've got positive absolute value in red, and it's facing up, negative absolute value in blue, and it's facing down, and then in green, this is the graph of x times cosine of 1 over x. So the graph of x, cosine 1 over x, never goes above the absolute value of x or below the negative absolute value of x. So graphically speaking, we can see that it really is in between those two functions, and therefore just start with that inequality. We can also see, again, like with the last one, that as x approaches 0 for both the positive absolute value and negative absolute value, those functions are approaching a y value of 0 as well. And that's squeezing this function. Look, it takes these really large values and squeezes them down. They're getting so tiny and forces them to go to 0 also, since this function, x cosine 1 over x, is sandwiched between the two. Now, one last comment I want to make is if I tried to evaluate this function at 0, so I tried to plug in 0 for x, I would end up with something that's undefined, because anytime you're trying to divide by x anywhere, even if it's just the inside of the function, that would end up being undefined, which is why we end up needing to use a different method to find limits for functions like this, because at 0 the function was undefined. So we would have had to have gone looking for an upper bound and lower bound function in order to do this squeeze theorem type question. And squeeze theorem type questions are often used a lot with trig functions because of the fact that they bounce around, right? They oscillate. And often we can find a function, two functions that they oscillate in between. So it's used a lot for trig functions. So that concludes this video. Thanks for sticking through all the way, and I'll see you in class.